Right now, a lock is forming over the central United States. 40 million Americans are about to live through something this weekend, and most of them don't know it's coming. The forecast is already public. The data has already been posted. NOAA wrote it down 4 days ago in a document that almost no one outside the forecasting community has read all the way through. The headline writers picked up the first half. They missed the second half. They missed the part that changes what the first half means. The last time this pattern formed here, it killed over 1,000 Americans in 5 days. That number is not a projection. It is not a model output. It is a body count from a real American city in a real American summer that you may remember. NOAA flagged a drought forming in the same states, the same week, in the same document, and nobody reported it. Not one major outlet covering the heat advisory this week mentioned the second forecast sitting directly underneath it on page 2. The two forecasts are not separate stories. They are the same story. They feed each other. And when they feed each other in the configuration that is forming right now, the result is not a hot weekend. The result is a trap. The atmospheric pattern driving this event has a name. That name is not in a single mainstream news article. It will be in this one. NOAA's own researchers documented this pattern in peer-reviewed literature decades ago. It was present in July of 1995 when the city of Chicago ran out of space in its morgue and parked refrigerated meatpacking trucks outside the medical examiner's office to hold the dead. It is present right now, sitting roughly 18,000 feet over the US-Canadian border, and it has not moved in a week. NOAA's own forecast discussion describes it as slow to weaken. That phrase is not a routine phrase. That phrase is a flag. By the end, you'll understand exactly what is forming and why it won't move. You will know the name of the pattern. You will know the names of the agencies tracking it. You will know what the next forecast update on June 4th will tell us. You will know what the US Drought Monitor release on June 5th will tell us. And you will know what the data from a 1995 American city says about the cost of an event exactly like this one when it sits over a populated region and refuses to move. Stay with me. July 12th, 1995. A stationary wall of hot air settled over the upper Midwest and would not move. No storms arrived. No cool front came. Chicago's overnight low on July 13th was 84 degrees Fahrenheit, providing no recovery from the 106-degree afternoon. Over 5 days, more than 1,000 Americans died across the Midwest and East Coast. In Chicago alone, 514 deaths were confirmed as directly heat-related. The city's medical examiner's office ran out of room. Refrigerated trucks were deployed as temporary morgues. That was not a hurricane. That was a still, silent week of heat in July. Right now, in Dubuque, Iowa, a 68-year-old retired schoolteacher named Margaret is living alone in a two-story house that her late husband built in 1971. The house has no central air conditioning. It has a window unit in the bedroom that she keeps off during the day to hold down the electric bill. The forecast for her county this coming weekend shows temperatures above 95 degrees Fahrenheit for 4 consecutive days. Margaret's neighborhood has no cooling center within walking distance. She doesn't drive at night anymore. Her adult children live in Phoenix and Dallas. Subscribe to Rupture because NOAA releases its next hazards outlook in 3 days, on June 4th, and the US Drought Monitor updates on June 5th. Both of those releases will either confirm what this forecast is showing or upgrade it to something more serious. We will be tracking every shift as it happens. You will want to be here when it does. Now, let's get into it. Part 1. What is forming? We're going to show you exactly what NOAA's official data says is building right now, city by city, day by day, and what it means. Part 1. What is forming? The air is not moving. That's the first thing NOAA's forecast discussion establishes before it says anything else about temperatures. At 3 in the afternoon on May 31st, 2026, a government meteorologist named Danny Barandiaran sat down at a terminal at NOAA's Climate Prediction Center in College Park, Maryland, and typed a sentence that described strong mid-level high-pressure building over the upper Mississippi Valley. He wasn't writing a warning. He was writing an observation. The pressure is already there. What sits in front of me on this screen is the document he wrote. The Climate Prediction Center calls it the CPC Hazards Outlook. The acronym is CPC, and from this point forward I'll use it that way, but you should hear what it means when I say it. The Climate Prediction Center. A division of NOAA that issues probabilistic forecasts for the United States out to 2 weeks. Their job is not to tell you tomorrow's high temperature. Their job is to look at the upper atmosphere and tell you what kind of week is coming, and what they wrote on May 31, 2026 is direct. They issued a slight risk of extreme heat. That's the formal designation. It means at least a 20% probability of temperatures exceeding the 85th climatological percentile and a 20% probability of reaching 90 degrees Fahrenheit or above during the window of June 8th through June 11th. 20% is not a coin flip. 20% is the threshold the agency uses to put a risk on the map at all. Below 20, they don't draw the shape. Above 20 they do, and they drew it. The shape they drew on May 31 covers a region that most Americans don't think of as a heat zone. It is not Phoenix, it is not Las Vegas, it is the northern and central plains, the upper and middle Mississippi Valley, the Ohio Valley, and the Great Lakes. 12 states, roughly. 40 million people, roughly. The states that grow the corn, the states that ship grain down the rivers, the states where retirees in older housing stock have spent their whole lives. And the shape NOAA drew on that map covers all of them. The exact official language matters here. I want to read it to you the way it appears in the document, because what's in it matters more than any paraphrase I could give. The CPC wrote, quote, "Increased potential of extreme heat continues across parts of the central and east-central contiguous US associated with strong mid-level high pressure centered over the upper Mississippi Valley," end quote. Read that sentence again in your head. Strong mid-level high pressure, centered over the upper Mississippi Valley. That is not the language of a passing warm spell. That is the language of a feature. Now let me translate what that designation actually means in plain English. A slight risk with 20% probability of exceeding the 85th percentile is not a general warmth advisory. It's a formal probabilistic forecast. NOAA has another tool called heat risk, and heat risk takes the CPC forecast and classifies it by what it does to people. For the core zone of this event, heat risk reads level 2 moderate. The agency's own definition of level 2 moderate is, quote, affecting those who are sensitive to heat, especially those without cooling or hydration, and some health systems and industries, end quote. Read that and stop. Without cooling, without hydration, health systems. That is not weather language, that is public health language. In Columbus, Ohio, a 72-year-old retired postal worker named Harold lives on the 3rd floor of a 6-story apartment building on the east side of town. His building's HVAC system was installed in 1989. Third-floor units on east-facing exposures accumulate heat throughout the day with no shade relief after noon. The June 8th through 11 forecast for Columbus shows daytime highs approaching 95 degrees Fahrenheit. Harold's building management has not issued a heat advisory. They've never issued one. On July 14, 1995, in a building 3 blocks away, a 74-year-old man was found dead in his apartment 4 days after the heat wave ended. Nobody had checked on him. His window had been closed the whole time. Multiply Harold by a fraction of the population in 12 states, and you start to see the actual shape of the exposure. The CPC didn't draw the map for buildings. They drew it for the air column above the ground. But the map and the buildings overlap. That overlap is where the risk lives. Older buildings in the upper Midwest were built for cold. They hold heat the same way they hold cold. A 1962 brick apartment building in suburban Minneapolis has a thermal mass that absorbs a day of 95-degree sun and radiates it back into the bedroom at midnight. The forecast doesn't tell you that. The buildings do. Here's where the document gets more specific. The CPC discussion references something called the GEFS, which is the Global Ensemble Forecast System. That's NOAA's primary medium-range probabilistic weather model. The GEFS doesn't run the forecast once. It runs it 31 times with slightly different starting conditions and looks at how the runs agree. When the runs agree, confidence is high. When they disagree, confidence is low. For this event, the GEFS runs agree on something specific. They agree that the heat criteria are maintained throughout the entire 2-week forecast window. Not just through the peak of June 8th to 11, through the back end of the window as well. The agency uses a specific phrase for that. They call it a long-lived event. 3 words. Long-lived event. Those 3 words mean the GFs is not seeing the heat ridge weaken on day 8, or day 10, or day 12. The GFS is seeing it hold, and when the GFS sees a ridge hold for that long, the CPC writes it down. That is the second most important sentence in the May 31st discussion, and it's the one the headline writers skipped. What Barandiaran's document says on page 2 is something the headline writers never reached, and it involves a second forecast that shares the same geography, the same 7-day window, and the same level of official concern posted in the same afternoon, in the same paragraph, by the same agency. I want to slow down on the geography for a moment, because the map matters as much as the dates. The CPC's Outlook map for June 8th through 11 shades the slight risk zone in a specific pattern. The core of the shading sits over Iowa, southern Minnesota, southern Wisconsin, northern Illinois, and northern Missouri. The outer edge of the shading extends into eastern Nebraska, eastern South Dakota, southern Michigan, Indiana, Ohio, western Pennsylvania, and the upper portions of Kentucky and West Virginia. That outer edge is not a soft edge. The outer edge means the 20% threshold has been crossed in those counties. The outer edge counties experience the event. They just experience it with a smaller margin. Inside the core, the picture is sharper. Des Moines, Iowa, Minneapolis, Minnesota, Madison, Wisconsin, Chicago, Illinois, Milwaukee, Wisconsin, Cedar Rapids, Davenport, Rockford, La Crosse. These are not desert cities. The population in these cities runs older than the national average in several specific neighborhoods, and the housing stock skews older than the national median by decades. The CPC map and the US Census housing age data, when laid over each other, show a specific overlap. The slight risk zone falls heavily on housing built before 1970. Housing built before 1970, on average, has less central air conditioning than housing built after 1980. The forecast didn't ask about that. The geography decided it. Let me give you the specific numbers on the population exposure. The 12 states the CPC outlined contain approximately 40 million residents inside the shaded zone, depending on which way you count the outer edge counties. Of those 40 million, the US Census American Community Survey data shows roughly 7.2 million are age 65 or older. That subset of the population is the one CDC's own mortality data identifies as carrying the highest per capita heat death rate of any age group. 40 million is the headline number, 7.2 million is the exposed number. The CPC didn't write the second number, the census did. The two datasets only meet when you lay them on top of each other. Here is the part of the May 31 document that takes the story past the headline. The CPC's discussion includes a section on Week 2 hazards, which extends from June 8th through June 14th. In that section, the agency writes that above normal temperatures are forecast to continue into Week 2 with only near normal precipitation favoured. Read that carefully. Near normal precipitation, not above normal precipitation, not a wet weather pattern arriving to break the heat, just near normal rain, under a long-lived heat ridge, with ground that came out of a wet spring and is now drying fast. That sentence is the bridge to part 2. The CPC wrote a forecast for the air. In the same paragraph, they wrote a forecast for the ground. The forecast for the ground has a name. The name is in a 3-letter acronym that I'll spell out in full when we get there. For now, just hold this. NOAA didn't issue a heat warning and a separate drought warning. They issued one document that contains both. The document is publicly available. The document was issued on May 31st, 2026, at 3 in the afternoon Eastern. The document has been online for 4 days as of this recording, and the document's second forecast has not been quoted in a single mainstream article covering the heat event. Before we move to part 2, consider why the CPC chose the language they chose. Government meteorologists don't write for drama, they write for record. Every word in a CPC discussion is reviewed by the duty forecaster, the forecast lead, and in some cases the branch chief. When the CPC writes strong mid-level high pressure centered over the upper Mississippi Valley, those words went through 3 sets of eyes before they reached the public document. The same is true of the phrase slow to weaken, which appears later in the same discussion and which we'll come back to in part 4. Government language is conservative by institutional design. When the language gets specific, it's because the data left them no choice. The GEFS isn't the only model the CPC consults. They also consult the European model, which the acronym is ECMWF, standing for the European Centre for Medium-Range Weather Forecasts. The ECMWF is operated out of Reading, England, and it has historically outperformed American models on medium-range forecasts in many evaluations. The CPC compares the GEFS and the ECMWF for every Week 2 outlook. When the two models agree, the forecast confidence rises. When they disagree, the CPC notes it. For this event, the May 31st discussion notes both models flagging elevated heat probability, but with a difference in the back half of the 2-week window. The GEFS holds the heat, the ECMWF weakens it slightly. That difference becomes the entire story of the June 4 update, which we'll reach in Part 6. One last thing about Part 1 before we close it out. The slight risk designation is one of 3 categories the CPC uses for its Week 2 extreme heat hazard. The 3 are slight, moderate, and elevated. Slight means at least 20% probability of crossing the threshold. Moderate means at least 40%. Elevated means at least 60%. The agency issues elevated heat designations roughly 14 times a year across all regions combined. That number, 14, is not a guess. It's the average from the agency's own archive going back to when the Week 2 hazard product began operations. 14 elevated designations a year. If the June 4th update upgrades this event from slight to elevated, it will be one of those 14. The agency does not throw that designation around. When they use it, the data has forced them to. There's one more piece of Part 1 that has to be on the table before we move. The CPC didn't issue this outlook in isolation. They issued it the same week the National Weather Service field officers in the affected region were briefing their own internal teams on the developing pattern. The NWS, the National Weather Service, is the operational arm of NOAA. Local NWS offices in Des Moines, Chanhassen near Minneapolis, Sullivan near Milwaukee, and Romoville near Chicago all run their own forecast offices. Each of those offices, by the end of the week of May 31st, had referenced building ridge amplitude in their internal forecast discussions. That language doesn't always make it into public Twitter posts or local news graphics. It sits in the technical forecast discussions that the offices publish daily, and that almost nobody outside the weather community reads. The local offices are the ones who will eventually issue heat advisories and excessive heat warnings if the event materializes as forecast. Those local level products are different from the CPC's national outlook. The CPC's outlook is the early signal. The local level products are the on-the-ground alerts. The two work together. The CPC says here is what is coming. The local NWS says here is what is happening. Right now, on June 1st, the CPC has said its piece. The local NWS offices have not yet issued their advisories because the event window is still 7 days out. That is the part the average viewer doesn't see. The forecast train is moving. The cars are not all on the track yet. The heat forecast is the story every meteorologist is covering this week. But on page 2 of NOAA's own technical document, there's a second forecast that none of them mentioned. Part 2 shows you what it says, what it means, and why the combination of the two changes the risk calculation for everyone in the affected states. Part 2, what nobody checked. The same document, the same paragraph. A second forecast, placed directly beneath the heat risk notice, that describes something happening to the ground while the heat happens to the air. NOAA calls it a rapid onset drought. The agency's exact language from May 31, 2026 reads, quote, "Therefore a possible risk of a ROD is posted," end quote. The acronym ROD stands for Rapid Onset Drought, in the same forecast window as the heat event, in the same states. Nobody reported it. Let me name what rapid onset drought actually is, because the term itself is the key to understanding why nobody outside NOAA flagged it. Rapid onset drought is not the slow agricultural drought your grandparents remembered from the 1930s. It is not the multi-year drought that builds over seasons in the American Southwest. Rapid onset drought is something newer in the meteorological vocabulary. It is an official NOAA classification for drought conditions that can develop within a single week. Not a season, not a month, a week. When above normal heat combines with below normal precipitation over soils that were recently adequate, the moisture deficit accelerates fast enough to flip the soil from sufficient to deficient in 7 to 10 days. The mechanism is straightforward once you see it. The ground stores moisture in the top few feet of soil. Plants pull moisture out of the ground and release it into the air through their leaves. The atmosphere pulls moisture out of bare ground through direct evaporation. When the air is hot and dry and the sun beats down on the ground for 10 or 12 hours a day without clouds, the rate at which moisture leaves the soil accelerates dramatically. Add in a vegetation layer that is actively growing and pulling water up through its roots, and the soil drains in days, not months, days. Here's what the CPC's May 31st discussion explicitly states, in its own words. Following a very wet spring, precipitation has been, quote, limited over the past several weeks, end quote, across the affected region. The same discussion notes that, quote, above normal temperatures are forecast to continue into week 2, with only near normal precipitation favoured." End quote. Put those two sentences side by side, and you have the textbook setup for rapid onset drought. Recently adequate soils, several weeks of limited rain, a heat ridge that holds for another 2 weeks, near normal rain that won't be enough to offset the evaporation. That is the recipe. NOAA didn't have to spell it out beyond the phrase rod because the analysts who read this document know what those 4 words mean in sequence. The historical reference point for this kind of event is 2012. The USDA Economic Research Service published a detailed report on the 2012 drought a year after it ended. The report documents that the 2012 rapid onset drought across the Corn Belt developed in a similarly compressed time frame to what the CPC is now flagging. It caused $30 billion in crop losses in a single growing season. That was the largest single-year agricultural loss in US history at that time. $30 billion in 1 year. Not because the drought lasted for years, because the drought arrived during the wrong 4 weeks of the corn growing cycle and amplified surface temperatures by an additional 2 to 5 degrees Fahrenheit above what the forecast models had projected. Outside Decatur, Illinois, a 5th-generation corn farmer named Dale has 340 acres in the ground right now at the V5 growth stage. The V5 stage is the 5th leaf stage of corn development. It is the most moisture-sensitive phase of the entire corn growing cycle. His county came out of May with soil moisture at 82% of capacity after the wet spring. He's checked his forecast app 4 times this week. It shows heat. It doesn't mention drought. The USDA's own crop moisture reports won't reflect the rod condition until after the US Drought Monitor updates on June 5th. Dale will not know the ground has crossed into abnormal dryness until he looks at the stalks. Now let's get specific about why the combination of heat and drought is more dangerous than either condition alone. The most important variable in surface temperature during a heat ridge is not the air mass, it's the ground underneath it. Moist soil absorbs solar radiation and releases it as water vapor, a process called evapotranspiration, which cools the surface the same way sweat cools skin. A forest floor on a 95-degree day feels 10 degrees cooler than a parking lot for exactly this reason. Dry bare ground does the opposite. Dry ground absorbs the same solar radiation but has no moisture to release. So instead of converting heat into water vapor, the ground stores the heat and radiates it back into the air column above it. That feedback amplifies surface temperatures by an additional 2 to 5 degrees Fahrenheit, above what the standard forecast model projects. 5 degrees doesn't sound like much in the abstract. 5 degrees on top of a 95-degree forecast is 100. 5 degrees on top of a 100-degree forecast is 105. The threshold where heat starts killing healthy adults in the open shifts dramatically in that range, and the threshold where heat starts killing vulnerable adults indoors shifts even more dramatically. The heat and the drought aren't 2 separate stories running at the same time. They're feeding each other, and that feedback loop has a name that appears in NOAA's own technical literature, and it still hasn't been said out loud in this video. The feedback loop runs in both directions. Heat dries the ground faster. Dry ground heats the air faster. Hot, dry air pulls more moisture out of the remaining soil. The remaining soil dries even faster. The air gets hotter still. That is a closed cycle with no off switch built into the system. The only mechanism that breaks the cycle is precipitation, arriving from outside the affected region, carried in by a weather system that pushes through the ridge. If no weather system pushes through, the cycle continues until the ridge itself breaks down. The ridge does not break down on a schedule. The ridge breaks down when the upper atmospheric pattern shifts. And the upper atmospheric pattern in this case has been described, in the CPC's own language, as slow to weaken. What's happening to Dale's 340 acres is happening on a different timescale than what's happening to Harold in Columbus, but it's the same mechanism. Harold's apartment building absorbs heat all day from a dry urban surface that radiates it back into his bedroom all night. Dale's corn absorbs heat all day from a soil profile that is losing moisture faster than the corn can pull it up through the roots. The corn enters water stress. The leaves begin to curl. The growing point inside the stalk slows its development. If the stress continues past 96 consecutive hours during the V5 to V8 window, the yield potential of the entire field drops by a percentage that the USDA's own crop modeling tools can quantify, and once that yield is lost, no amount of late-season rain brings it back. The DTN Progressive Farmer, which is one of the agricultural industry's longest-running daily reporting outlets, confirmed on May 28, 2026, that a drier pattern is setting up through mid-June across the Midwest. that is 3 days before the CPC's official discussion. The agricultural community was watching this setup before the meteorological community wrote it down. The two communities used different data feeds and different language, but they were looking at the same upper atmospheric pattern. The farmer saw the soil moisture trend. The meteorologist saw the ridge amplification. The two are connected by physics, and the physics doesn't care which community wrote the first article. Now let me say what the mainstream news coverage of this week has and has not connected. Every major outlet that covered the heat advisory this week mentioned the temperatures. Several mentioned the geography. A handful mentioned the historical comparison to 1995. Not one mainstream article connected the heat forecast to the ROD forecast, posted in the same CPC document. That is not an accusation. That is just an audit. The two forecasts share the same document, the same paragraph, the same week, and the same states. Linking them together is what the document itself does. The headline writers either didn't read past page 1, or they read past it and didn't recognize what the second forecast meant in combination with the first. Here's what the combination means in terms of risk profile. When the National Weather Service issues a heat advisory based on a temperature forecast, that advisory is calibrated to a baseline assumption about surface conditions. The baseline assumes normal soil moisture and normal vegetation cover. When surface conditions deviate from baseline, the advisory underpredicts the actual heat experienced at the ground level by 2 to 5 degrees Fahrenheit. That gap is not a forecast error in the traditional sense. The model forecasted the air mass correctly. The air mass interacted with a non-baseline surface, and the surface added heat the model didn't account for. The advisory will still say 95. The thermometer on the porch will read 19. The body will feel 100. In an apartment with no central air conditioning, the indoor temperature during a sustained outdoor heat event tracks the outdoor temperature with a lag of several hours and a peak offset of 0 to 5 degrees, depending on the building's insulation, window orientation, and ventilation. An indoor temperature of 95 to 100 degrees, held for multiple consecutive nights without recovery, is the specific condition that drove the 1995 mortality data we'll examine in detail in Part 5. The advisory threshold and the indoor mortality threshold are not the same number. The 2 to 5 degree drought amplification widens the gap between them. The US Drought Monitor, which I'll call the Drought Monitor from here on, is operated jointly by NOAA, the USDA, and the National Drought Mitigation Center at the University of Nebraska-Lincoln. It updates every Thursday morning at 8:30 Eastern. The next update arrives on June 5th. The June 5th release will be the first official confirmation, or non-confirmation, of whether the ROD condition has registered in the soil moisture data across the upper Midwest. If the map turns yellow across the core of the heat zone, the ROD has begun. If it doesn't, the ROD is still in the forecast phase, and the heat ridge has another week to drive it into the data. Before we move to Part 3, 2 more pieces of context need to be on the table. The first is what the Palmer Drought Severity Index, the PDSI, looks like in this region heading into the event. The PDSI is a long-standing drought index that integrates temperature and precipitation departures over months, not weeks. The current PDSI for the upper Mississippi Valley sits in mildly positive territory after the wet spring. That is what the CPC was referring to when it described recently adequate soils. The rapid onset drought classification doesn't require a negative PDSI to begin. It just requires the trajectory. The PDSI updates monthly, which means by the time the index reflects the ROD, the event will already be visible in every other agricultural data feed. The second piece is the role of the jet stream in all of this. The jet stream is the high-altitude river of fast-moving air that separates cold polar air from warmer subtropical air. When the jet stream runs straight from west to east, weather systems track across the country in normal succession. When the jet stream develops a large northward bulge called a ridge, the bulge anchors a high-pressure dome underneath it. Storms get deflected around the bulge. Cool air gets pushed north of the bulge. Whatever sits inside the bulge stays inside the bulge. The CPC's May 31st discussion describes a strong mid-level high-pressure system over the upper Mississippi Valley. That system is the surface expression of an enormous northward bulge in the jet stream. Until the jet stream pattern changes, the bulge stays where it is. The third piece, briefly, is what isn't in the CPC document but is in the agricultural data. The USDA's National Agricultural Statistics Service publishes weekly crop progress reports. The report from the week ending May 25th showed corn emergence at 87% across the major corn states, With most of the crop in the V3 to V5 stage, that is the most moisture-sensitive growth window of the entire season. The CPC's ROD forecast lands directly on top of that growth window. 40 million people are exposed to the heat side of this event. The corn crop is exposed to the drought side. The two exposures are not on the same calendar, but they are in the same forecast. In late July of 2012, when the rapid onset drought peaked, 65% of the contiguous United States was in some level of drought. The drought monitor only goes back to 1999. That 65% was the highest number in its history. The 2012 event also coincided with a heat ridge that drove temperatures into the upper 90s and low 100s across the central United States for an extended window. The combination of the ridge and the rod in 2012 is the closest modern analogue to what NOAA's May 31st document is now flagging for June of 2026. The 2012 event also produced documented heat mortality, though at a lower count than 1995 because 2012's ridge moved more than 1995's did. The current ridge, per NOAA's slow-to-weaken language, is not moving on the timeline 2012's did. Heat-amplifying drought and drought-amplifying heat is the first part of a larger feedback cycle, but it's still not the most important thing happening in the upper atmosphere right now. Part 3 introduces the third factor, the one that determines whether the power grid holds when 40 million people reach for their thermostats at the same time on the same afternoon. Part 3. What comes next? It's 4:30 in the afternoon on June 9th. The temperature in Omaha is 97 degrees Fahrenheit. The forecast says it's going to be 96 tomorrow and 95 the day after that. Every air conditioner in every house in a 12-state region turned on at approximately the same hour. The grid is managing, for now. NERC, the organization that monitors North American power reliability, released its 2026 Summer Reliability Assessment on May 19th. What it says about the coming weeks is in this part. NERC stands for the North American Electric Reliability Corporation. It is the non-profit regulatory authority that oversees the bulk power system across the United States, Canada, and a portion of Baja California and Mexico. NERC doesn't operate the grid. The grid is operated by regional transmission organizations and individual utilities. NERC sets the reliability standards and audits whether the system can meet projected demand. Every May, NERC publishes its Summer Reliability Assessment, which forecasts whether the grid has enough capacity to meet the summer's expected peak demand. The 2026 assessment was published May 19th. The headline number in the report is positive. NERC documents that the grid has added 58 gigawatts of new capacity since the previous summer's assessment. That is the largest single-year capacity increase in the assessment's history. That sounds like good news. The headline reads like good news. Most coverage of NERC's report ran with the 58 gigawatt number and moved on. But the same report contains a second sentence, and the second sentence is what matters for this week's forecast. NERC writes, quote, "Extreme heat events remain the primary threat to system reliability across North America, and some parts of the US are still at elevated risk of blackouts this summer, meaning electricity supply could fall short of demand during more intense, persistent or widespread heat." End quote. The Pacific Northwest carries the highest elevated risk designation in the 2026 report. The Upper Midwest, which is the core of the current heat event zone, carries a moderate risk designation. Moderate is not zero. Moderate is a specific category in NERC's framework that flags potential supply gaps under extreme demand conditions. Now let me explain why a multi-day heat event is categorically different from a single-day temperature spike when it comes to the grid. NERC's reliability models calculate peak demand for one extreme day. The model takes the hottest expected day, runs the demand projection, and compares it to available supply. If supply exceeds demand, the system passes the model. That is how the assessment is structured. What the model is not optimized for is a stationary heat event that produces elevated demand for 4 to 6 consecutive days. Each consecutive high-demand day exhausts more reserve margin. Each consecutive day stresses transformer capacity in ways that compound. Each consecutive day increases the cumulative probability of equipment failure somewhere in the system. In suburban Minneapolis, a 66-year-old retired nurse named Carol depends on a powered medical device. She uses a CPAP machine and a portable oxygen concentrator that must run continuously overnight. Her home is on a residential grid line that serves 340 houses in a neighborhood built in 1962. The transformer serving her block is original equipment. During the extended heat event of August 2012, a transformer failure on that same grid line blacked out 220 homes for 31 hours. Carol has a 4-hour battery backup. She doesn't know what comes after that. She's planning a weekend trip to her daughter's house. She hasn't checked the forecast. The air is not moving, and neither is the water. Hold that phrase for a second, because it's not rhetorical. The air, in the upper atmospheric sense, is locked under the high-pressure ridge that the CPC described. The water, in the soil moisture sense, is leaving the ground faster than it's being replenished, and the drought monitor will show the trend on June 5th. Both systems are now in the same compounding loop. Heat dries the ground, dry ground heats the air. The combined heat increases the load on every air conditioner connected to the grid in the affected states. The grid responds by drawing more power from generation sources that, in some cases, also depend on water. Thermal power plants use water for cooling. When water supplies tighten and air temperatures rise simultaneously, the efficiency of thermal generation drops. The same plants that need to produce more power to meet demand produce less power per unit of fuel because their cooling water is warmer. Here's the specific interaction the NOAA report doesn't fully model, but does flag. Crops stressed by heat and dryness consume more groundwater through irrigation. Municipal water systems pump more to compensate for irrigation draw and residential consumption. Water pumping stations are themselves grid customers. They draw more electricity. Hospitals run their cooling systems harder. Hospitals are also grid customers, and many run on a tier of priority service that other customers don't have. All of that load lands on the same grid. Grid demand rises beyond residential peak-only projections, and reserve margins narrow in exactly the states most exposed to the heat. 3 systems: heat in the air, drought in the ground, strain on the grid. And none of the coverage this week has explained why all 3 are happening simultaneously, in the same place, in the same week, because nobody covering it knows what atmospheric pattern is holding them all in place. NOAA's report acknowledges the limits of its own modelling. The report includes a section on what the agency calls operational risks during prolonged events. The language in that section is careful. NOAA writes that the system is designed to meet projected peak demand, and that the system has historically met that demand in the vast majority of summer events. But the report also notes that the frequency of multi-day extreme heat events has increased over the past 2 decades, and that the reliability of older transformer infrastructure under cumulative stress is, quote, an area of ongoing study, end quote. An area of ongoing study, in NOAA's institutional vocabulary, means the answer is not yet known, with the level of confidence the agency requires before publishing a definitive forecast. That phrase is the agency's way of telling you they don't yet have a clean number. Let me put a sharper edge on what the grid actually does during a sustained heat event. The grid is a real-time system. Electricity has to be generated at the moment it is consumed. There is no large-scale storage layer that smooths out demand peaks across multiple days. Battery storage is growing, but still represents a small fraction of total grid capacity. So when 40 million people reach for their thermostats at the same hour on the same afternoon, the generation side of the grid has to ramp up immediately to match. The fastest ramping is done by natural gas peaker plants, and increasingly by battery discharges. Coal plants take hours to ramp. Nuclear plants run at constant output. The peakers and the batteries are the swing capacity. When the peakers are all running and the batteries are all discharged, the grid has reached its limit. In the affected region, the generation mix includes a significant fraction of coal and nuclear baseload, a smaller fraction of natural gas, and a growing fraction of wind and solar. Wind output in the upper Midwest during a stationary high-pressure event tends to be low because high-pressure systems suppress surface winds. Solar output is high during the day but drops to 0 at night. The grid's evening peak, which typically runs from 5 DUI PM to 9 PM Central, is the most stressed window of the day. Solar is already declining or off. Wind is at baseline. The thermal plants are running near maximum. Demand is high because people are home and air conditioners are still running hard against the day's accumulated heat. That window is where the failures, when they happen, happen. What NOAA's reliability models project with confidence is that the grid will meet projected peak demand under normal summer conditions. What they cannot project with confidence is how many consecutive high-demand days the system handles before cumulative stress produces cascading failures in older infrastructure. The transformers serving 1962 neighborhoods like Carol's are not the same equipment as transformers in newer developments. The 2012 heat event in the upper Midwest produced documented transformer failures across multiple utility territories, with some of the failures occurring on day 4 or day 5 of the event, not on day 1. The cumulative stress curve is real. It just doesn't have a published formula. The compounding interaction is what makes this part different from a standard grid story. A normal grid story examines one variable. This story has 3. Heat that won't leave, drought that arrives during the heat, grid demand that runs at elevated levels for 4 to 6 consecutive days because of both. NERC's report acknowledges the heat variable. The drought monitor will report on the drought variable on June 5th. No single agency report integrates all 3. The viewer has to integrate them. That is what we're doing here. The CPC's discussion does not directly reference NERC. The NERC report does not directly reference the June 8 to 11 event. The 2 documents were written for different audiences by different agencies on different timelines, but they overlap on the same physical reality. The same atmosphere that drives the heat advisory drives the grid demand. The same drought that amplifies the heat tightens the water supplies that the grid depends on. The connection lives in the physics, not in the document trail. In Phoenix, the average household uses about 28 kilowatt-hours of electricity per day during summer peak conditions. In the upper Midwest, the average is closer to 22 kilowatt-hours during summer peak, because the historical baseline doesn't include sustained extreme heat. The gap between the two is the demand surge that arrives during an event like the one now forming. 40 million people drawing an extra 4 to 6 kilowatt-hours per day each adds up to a regional demand increase that the grid can absorb on day 1. The question is how it absorbs the same increase on day 4, day 5, and day 6, with reserve margins narrowing each day. The honest uncertainty here is important. NERC is not predicting a blackout. NERC is publishing a reliability assessment that flags elevated risk in specific regions under specific conditions. The conditions matching the elevated risk profile are exactly the conditions the CPC is forecasting for June 8 through 11. That overlap does not guarantee a failure. It identifies a risk window. The risk window is real. Whether the window produces an actual outage depends on equipment behavior that no agency models with full precision. What we can say with confidence is what happened during prior comparable events. The August 2012 heat event produced rolling blackouts in parts of the upper Midwest and grid alerts across multiple regional transmission organizations. The July 2011 heat event in Texas produced similar grid alerts and consumer-level conservation requests. The July 2019 heat event in the Mid-Atlantic produced an emergency demand response activation in PJM, the regional transmission organization that covers a large portion of the eastern interconnection. None of those events produced full-scale grid collapse. Each of them produced localized failures, voluntary conservation requests, and equipment stress that the operators absorbed with margin to spare. The margin varied from event to event. The current event's margin is not yet known. Every one of the 3 systems described in this part, the heat, the drought, and the grid strain, is being sustained by a single atmospheric configuration that has been sitting in NOAA's own technical literature for decades. That configuration has a name. Part 4 says it out loud. One last context block for Part 3 before we move. The grid in the affected region is operated by a combination of regional transmission organizations. The Mid-Continent Independent System Operator, abbreviated MISO, covers most of the core heat zone, including Iowa, Minnesota, Wisconsin, Illinois, Indiana, and portions of surrounding states. PJM Interconnection covers Ohio, Pennsylvania, parts of Michigan, and the Mid-Atlantic. The Southwest Power Pool, abbreviated SPP, covers the Central Plains. Each of these operators runs its own reserve margin calculations, its own demand projections, and its own emergency response protocols. The 3 operators coordinate on cross-border power flows when one region needs to import from another. During a regional heat event, the affected operators can request emergency assistance from neighboring operators. When the heat event covers all 3 operators simultaneously, which is what the current forecast projects, the assistance window narrows. There's nowhere to import from because the neighbors are also stressed. That is the specific scenario NERC's report flags as the highest risk failure mode for multi-day continental scale events. The current event sits in that exact failure mode. The forecast covers MISO, PJM, and SPP in the same window. The assistance mechanism that operators rely on during single region events is structurally less available during continental events. That's the third system in motion. The grid response capacity is itself a function of how widespread the event is. The wider the event, the less assistance is available. The CPC's geographic footprint for June 8 through 11 covers all three major grid operators. The wider footprint is what makes this different from a typical regional heat event. It's also what makes the next part necessary. Three systems under simultaneous stress, one mechanism sustaining all three. That mechanism has a name. It has been in the scientific literature for years. Almost no one outside the forecasting community is saying it. We're going to say it now. Every one of the three systems described in this part, the heat, the drought, and the grid strain, is being sustained by a single atmospheric configuration that has been sitting in NOAA's own technical literature for decades. That configuration has a name. Part 4 says it out loud. Part 4. What locked it in everything in the first three parts of this video, the heat, the drought, the grid pressure, has a single explanation. It's been in NOAA's forecast discussion since May. It appears in peer-reviewed scientific literature going back decades. It was present in July 1995, when over 1,000 Americans died, and it is sitting directly overhead right now. The mechanism driving all of this has a name. It has been in the scientific community for years. Almost no one outside the forecasting community is saying it out loud. We're going to say it now. The mechanism driving this event is called an omega block. The upper atmosphere, roughly 18,000 feet above the surface, has locked into a shape that resembles the Greek letter omega. A dome of high pressure sits at the center, flanked by two low-pressure systems on either side. That shape acts like a physical lid. No storms can push through from the west. No cool air can arrive from the north. Whatever heat is under it stays under it, and the configuration sustains itself. This is why the heat forecast in Part 1 described a long-lived event rather than a passing spike. The Jeffs model recognized the omega block structure and projected it would maintain itself for the full 2-week window. This is why the rapid onset drought in Part 2 is not a side effect arriving later. The omega block blocks precipitation as completely as it blocks cold air, accelerating soil drying from the first day of the event. This is why NERS's grid concern in Part 3 isn't about a single afternoon peak. It's about a stationary system that holds elevated demand in place for days, not hours. NOAA's CPC discussion issued May 31, 2026, uses the exact phrase, slow to weaken high pressure spanning most of the US-Canadian border. That is the agency's operational description of an omega block in place. The May 25, 2026 precursor event over the Canadian prairies confirmed the block was already forming 1 week before the US event begins. Now, you know what you're looking at. Let me walk through the science behind the omega block because the name alone doesn't carry the full picture. The upper atmosphere, the layer where the jet stream lives, is a fluid system. It moves. It has waves. The waves are the result of how the jet stream meanders around the planet, pushed by temperature contrasts between the equator and the poles. Most of the time, those waves move from west to east at a steady rate, and weather systems move with them. Storms come and go. Cold fronts arrive and pass. The pattern cycles through. But the jet stream can develop a specific configuration where the waves stop progressing. The waves anchor in place. A ridge, which is a northward bulge of warm air, sits in one location, flanked by two troughs, which are southward dips of cold air on either side. When the configuration is symmetric and stable, the three features lock together. The ridge can't move east because the trough to its east is in the way. The ridge can't move west because the trough to its west is in the way. The atmosphere stalls. The Greek letter omega is the visual shape the pattern makes on an upper atmospheric map. A central dome with two flanking depressions, hence the name. NOAA's Atlantic Oceanographic and Meteorological Laboratory, which I'll call AOML, published a peer-reviewed study in 2019 in a scientific journal. The study examined how upper-level anticyclonic blocking patterns over the Great Plains affect long-term weather conditions. The study's own language matches what we're seeing right now almost exactly. The researchers wrote that these blocking patterns, quote, serve as a blocking pattern for transient storms and are supportive of persistent drought and clear sky conditions, end quote. Read those two pieces of language side by side. The IML study from 2019 used the phrase supportive of persistent drought. The CPC's May 31, 2026 discussion forecasts a rapid onset drought, under a slow-to-weaken high. Same mechanism, same language, 7 years apart. In St. Louis, Missouri, a 61-year-old dialysis patient named James reports to a clinic 3 mornings a week. His treatment takes 4 hours. The clinic is air-conditioned. His apartment is not. He uses a single window unit in his bedroom and keeps the living room closed during the day. On July 14, 1995, in a city 300 miles north of St. Louis, a dialysis patient who missed 2 consecutive treatments during the heat wave because the transport service suspended operations died of heat-related kidney failure. James's transport service has no heat contingency protocol. The Omega block forming overhead doesn't care about transport schedules. The July 1995 Chicago heatwave was driven by an identically configured stationary upper-level, high-pressure ridge over the same geographic region. The NWS Forecast Office in Milwaukee maintains a historical record of that event. The record confirms the mechanism in 3 specific terms: the ridge-blocked cloud formation, the ridge-trapped surface heat with no removal mechanism, the ridge-prevented overnight temperature recovery. Those 3 characteristics are exactly what NOAA's CPC describes in its May 31, 2026 document for the current event. The match is not approximate, it is specific. 3 characteristics in 1995, 3 characteristics in 2026, same 3. Let me ground this in the current model output, the CPC's own probabilistic extremes tools, which run on data from both the European model, the ECMWF, and the American model, the GEFS, show at least a 20% probability of temperatures exceeding the 85th climatological percentile across the northern plains eastward through the Ohio Valley for the entire 2-week forecast period. The GEF specifically flags this as a long-lived event. The persistence is the Omega block's operational signature. A passing ridge doesn't produce a long-lived signal. An Omega block does. The model isn't telling us that the heat will last because of some abstract probability. The model is telling us the upper atmospheric pattern is locked, and as long as it stays locked, the heat stays. The near-term forecast implications go in 2 directions, and both directions depend on what the June 4 CPC update shows. If the June 4 update reveals model convergence toward the GEF's long-lived scenario, with the ECMWF moving closer to the GEFs rather than the GEFs softening toward the ECMWF, the slight risk designation will upgrade. It will upgrade to moderate, which corresponds to at least 40% probability, or to elevated, which corresponds to at least 60% probability. An elevated designation is something NOAA issues roughly 14 times per year across all regions combined. That number, 14, is the operational rarity threshold. 14 events a year nationwide. If this becomes one of them, that fact alone will be the lead story of the next week. The honest uncertainty here is the duration question. The Omega block explains why the event will persist. It does not precisely predict how long before the block breaks down. Historical Omega blocks over the central United States have lasted between 5 days and 21 days. The 1995 Chicago event lasted 5 days because the block over that region broke on day 5. Other documented Omega blocks have held for much longer, including a 2003 event in Europe that lasted over 2 weeks and produced over 70,000 excess deaths across the continent. The difference between a 5-day event and a 21-day event in the same geography, with the same grid and agricultural exposure, is not a matter of degree. It is a categorical difference. What NOAA's models can't yet confirm is whether the block will begin weakening by June 12th or whether it will hold through the end of the month. The June 4th forecast update will narrow that range. But the honest answer right now is that the atmospheric pattern overhead has not yet shown any signal of self-correction. NOAA's own guidance describes the high pressure as slow to weaken. That phrase in a forecast discussion is not routine, it is a specific flag. July 1995 lasted 5 days. The current Omega block precursor formed a full week earlier than the 1995 event's precursor did. The GEFS model's long-lived signal projects it across the full 2-week forecast window. 5 days and 21 days are not the same story. Let me put more detail on the precursor. An Omega block doesn't appear instantly. It develops through a sequence of upper atmospheric adjustments that meteorologists can track in the days leading up to its full formation. The May 25, 2026 precursor event over the Canadian prairies was the first visible signal that the jet stream pattern was setting up into an Omega configuration. By May 28th, the ridge over the Central Plains had begun amplifying. By May 30, when the CPC wrote its discussion, the configuration was identifiable enough for the agency to write slow to weaken into the public document. The configuration has now had a week to consolidate. A week of consolidation is significant in upper atmospheric terms. The longer a blocking pattern holds, the more energy it accumulates, and the harder it becomes to break. The braking mechanism for an omega block is not internal. The block doesn't break itself. The block breaks when an external disturbance, usually a strong cold front pushing in from the Pacific Northwest or from Canada, has enough energy to disrupt the symmetry of the omega shape. Without that external disturbance, the block holds. The current forecast guidance, looking out 2 weeks, doesn't show a clear disrupting feature. There's a possibility of pattern adjustment in the back half of week 2, but that possibility is exactly the difference between the GEFS and the ECMWF. The GEFS sees no disruption. The ECMWF sees a weak one. The June 4 update will tell us which model is right. The 2003 European event I mentioned is worth holding for a moment because it's the most extreme omega block in the modern record. That event sat over France, Germany, Italy and surrounding countries for most of August 2003. Paris reached temperatures over 100 degrees Fahrenheit for consecutive days, with overnight lows above 75 degrees Fahrenheit. The death toll across Europe was estimated at over 70,000 from the World Health Organization's retrospective analysis. France alone counted nearly 15,000 excess deaths. The event broke when the jet stream finally shifted in early September. The reason that number matters is not because the US will see 70,000 deaths from this event. The reason it matters is that an omega block, when it locks over a populated region with vulnerable demographics and inadequate cooling infrastructure, produces death tolls that scale with duration in a nonlinear way. 5 days produces a count in the hundreds. 2 weeks produces a count in the tens of thousands. The shape of the mortality curve is not flat. It accelerates. The American mortality data from 1995 illustrates the same curve at a smaller scale. The first day of the Chicago heat event produced relatively few documented heat deaths. The second day produced more. The third and fourth days produced the bulk of the count. By the fifth day, the medical examiner's office was processing more bodies than it could store. The reason the death curve accelerated is exactly the mechanism I described in the hook. Overnight lows didn't drop. The body couldn't recover. Heat stress accumulated across consecutive nights. Vulnerable adults who survived day 1 and day 2 didn't survive day 4 and day 5. The 1995 event broke on day 5. If it had continued through day 7 or day 10, the count would have been higher in a nonlinear way. The current event's forecast window is June 8 through 11 for the peak, with the long-lived signal extending through the back half of June. If the block holds through June 18th or beyond, the US mortality data will track the European curve more than the 1995 American curve. That is not a prediction. That is a description of what the curve looks like at different durations. Whether this event reaches those durations depends on the June 4th CPC update and the June 5th Drought Monitor update. 2 data points, 24 hours apart, both due in 3 days. One more piece of evidence belongs here. The 2019 AOML study I referenced earlier didn't just describe omega block patterns, it also analysed how often these patterns produce concurrent heat and drought events over the central United States. The study found that, in the historical record, roughly 60% of multi-day omega block events over the Central Plains produced documented soil moisture deficits within 10 days of pattern onset. 60%! That is the base rate from the published literature. The rapid onset drought forecast in the CPC's May 31st discussion is consistent with that 60% base rate. It's not a surprise event. It's the expected outcome of an omega block configuration in this geography at this time of year with these antecedent soil conditions. Before we move to part 5, 2 more pieces about the omega block need to be in the record. The first is what the upper atmospheric maps actually show right now. NOAA's Weather Prediction Center publishes 500 millibar height analyses every 6 hours. The 500 millibar level is the standard upper atmospheric layer meteorologists use to identify ridges and troughs. The current 500 millibar analysis for North America shows a clearly defined ridge centered approximately over the upper Mississippi Valley, with 2 flanking troughs, one over the Pacific Northwest and another over the Canadian Maritimes. That is the textbook omega block configuration. The map doesn't require interpretation. It's visible to anyone who can read a 500 millibar chart, which is a standard professional product the agency publishes every 6 hours, around the clock. The second piece is what the historical climatology says about omega blocks in June over the United States. June omega blocks are not the most common type. The most common omega blocks in the historical record occur in July and August, when the jet stream sits at its most northern latitude and the contrast between subtropical and polar air is strongest. June omega blocks are less frequent, which is part of what makes this event notable. A June omega block typically forms in association with an unusually deep ridge amplitude and an unusually persistent jet stream pattern. The current event has both. The amplitude is high, the persistence is documented across multiple model runs. June is early for this type of pattern, and early is the part that matters for the season ahead. If the block holds into July, the seasonal context shifts. The mortality risk profile shifts with it. Understanding what the omega block is explains the mechanism. Understanding what it did in 1995, city by city, hour by hour, body by body, is part 5. What happened in Chicago over those 5 days in July 1995 is the only complete record we have of what an omega block event costs when it locks over a populated American city, and that record is more specific than anything you've read in a news article this week. Part 5. What 1995 showed by July 13, 1995, the overnight low in Chicago had not dropped below 80 degrees Fahrenheit for 2 consecutive nights. The human body recovers from heat stress during the night. When the night doesn't cool, the body carries accumulated heat stress into the next day's peak. By the third night, the accumulation doesn't recover. The medical literature calls this excess heat stress accumulation. The people living through it in 1995 didn't have a name for it. They just stopped waking up. The numbers from July 12 through 16, 1995 are not estimates. Official records confirm every one of them. Over 1,000 deaths across the Midwest and East Coast in 5 days. In Chicago alone, 514 confirmed heat-related deaths. The peer-reviewed study published in the American Journal of Public Health later documented 696 excess deaths for the city, which is a slightly larger number that accounts for deaths during the event that may not have been formally classified as heat-related at the time, but were attributable to the event when analysed statistically. The Cook County Medical Examiner's Office processed more bodies in those 5 days than it had in any comparable period in its recorded history. Refrigerated trucks from a meatpacking company were parked outside the morgue as temporary overflow storage. That detail is not folklore. It is in the official record of the event. On July 15, 1995, a home health aide named Rosa arrived at the Lawndale apartment of a 77-year-old retired factory worker named Eugene at 8:30 in the morning. She had not been able to reach him by phone the day before. She found him in his recliner in the living room, fully dressed, with the windows closed. The apartment had no air conditioning. The indoor temperature was 109 degrees Fahrenheit. Eugene had survived the Korean War, a factory fire in 1961, and a heart attack in 1988. He did not survive 4 days of an omega block in July. His name appears in the Cook County Medical Examiner's records as one of 514 confirmed heat-related deaths. He is one number in a count that reached 1,000 before the week was over. The NWS Milwaukee historical record of the 1995 event documents the meteorological mechanism in clinical language. The record identifies 3 specific characteristics that define the event: stationary upper-level high-pressure blocking storm passage, surface heat trapped with no removal mechanism, overnight low temperatures remaining above 80 degrees Fahrenheit preventing physiological recovery. Those 3 characteristics are identical to the configuration the CPC now projects for June 8 through 11, 2026. Not similar, identical. The same 3 mechanisms in the same geography, 3 decades apart. The intervening years have not changed the physics of how an omega block works. Let me walk through what the 1995 mortality data revealed about who died and why. The peer-reviewed study by Whitman and colleagues, published in 1997 in the American Journal of Public Health, examined every documented heat-related death in Chicago during the event and analysed the risk factors statistically. The findings were specific. Adults living alone carried an odds ratio of 2.3 for heat-related death compared to those living with others. That number means that, controlling for other factors, an adult living alone was 2.3 times more likely to die during the event than an adult living in a household with other people. Adults without working air conditioning had a protective factor nearly 3 times worse than those with it. Adults aged 65 and older represented the highest per capita mortality rate of any age group. That last finding has not changed. The CDC's own data from 2004 through 2018, published in the agency's Morbidity and Mortality Weekly Report, confirms that adults aged 65 and older still represent the highest per capita heat death rate of any age group in the United States. The percentage of all US heat deaths that occur in adults 65 and older has held steady at approximately 39% across 2 decades. That is the published number. Almost 4 out of every 10 heat deaths in the country happen in the population segment that is most exposed to the current event. The combined data, 1995 and 2004 through 2018, tells one story. The story is that the demographic risk profile for heat events has not shifted in any meaningful direction since the data became reliable. What does that mean for the current event? The June 8 through 11 heat window is targeting the same geographic region as 1995, with a larger exposed population than 1995. The 12 states in the current CPC zone contain more residents in absolute terms than the same states held in 1995, and the proportion of adults aged 65 and older has increased significantly. In 1995, adults 65 and older were approximately 12.8% of the US population. By 2025, that share had grown to approximately 17%. The aging of the population since 1995 means the demographic vulnerability to heat events has grown structurally, not shrunk. There are more people in the highest risk group today than there were in 1995, in both absolute and relative terms. Layer that demographic shift on top of the housing stock, and the result becomes specific. The US Census American Community Survey data shows that approximately 86% of US households have some form of air conditioning, which is up significantly from 1995 levels. But the distribution of that 86% is not uniform. In specific neighborhoods in older upper Midwest cities, the share of households without central air conditioning is substantially higher than the national average. Older multifamily buildings in cities like Chicago, Milwaukee, Minneapolis, and Cleveland often have window units only, or no cooling at all, especially in lower-income census tracts. The 1995 event killed disproportionately in those exact neighborhoods. The current event is forecast for the same exact neighborhoods. The air is not moving, the water is disappearing, and NOAA just told you both in the same sentence. Hold that phrase for a moment, because part 5 is the moment all 3 dimensions come together. The atmospheric lock is the omega block. The drought is the rapid onset drought forecast posted in the same document. The institutional gap is the silence from mainstream coverage, which has reported the heat but not the combination. 3 dimensions, 1 document, 4 days of public availability. And the public, the 40 million people in the affected zone, has been hearing about heat in isolation, when the document itself describes heat in combination with drought, under a slow-to-weaken atmospheric lid. The grid context from Part 3 layers on top of this. The August 1995 event also produced documented power failures in Chicago, including blackouts in low-income neighborhoods that disproportionately affected exactly the demographic groups the Whitman study identified as highest risk. Adults living alone, in older buildings, without working air conditioning, in neighborhoods where the grid failed during the peak of the event. That intersection was not modeled. It happened. It happened to specific individuals. The Whitman study documented it after the fact. The current event has a higher baseline grid load than 1995 had, and the housing stock and demographic vulnerability are arguably worse, not better. Whether the grid holds during the current event is one of the open questions Part 3 identified. Whether the demographic vulnerability has improved is a question Part 5 just answered. The answer is no. The 1995 event lasted 5 days because the omega block broke on the 5th day. The current omega block formed a week earlier in the season, with a stronger precursor signal, and NOAA's own models describe the high pressure as slow to weaken. The question isn't whether this will be like 1995. The question is whether 5 days is the ceiling or the floor. Let me put one more specific number on the table from the 1995 record. The Illinois Department of Public Health documented that emergency department visits in the Chicago metropolitan area increased by 35% during the peak days of the event. Hospital ICUs in the affected hospitals ran at or near capacity for the duration of the event. Some hospitals diverted ambulance traffic to other facilities. Some facilities cancelled elective procedures to free bed space. That 35% number is not a soft estimate. It is from the State Health Department's After Action report, which examined the operational stress on the regional healthcare system during the event. The current Upper Midwest healthcare system has different capacity characteristics than the 1995 system had. Hospital beds per capita in some Upper Midwest states have declined since 1995 due to consolidation and closures. Rural hospitals in particular have fewer beds and longer transport times to tertiary facilities than they had in 1995. The ICU capacity in many regional facilities is also lower in relative terms. A 35% ED volume increase under current capacity conditions would produce more strain in many specific facilities than the same volume increase produced in 1995. That doesn't mean the system fails. It means the system has less margin than it had 3 decades ago in the same region, facing the same kind of event. The combined evidence, the meteorological match with 1995, the demographic shift toward higher vulnerability, the housing stock that hasn't improved in the affected neighborhoods, the grid baseline that is higher than 1995, the healthcare capacity that is tighter than 1995, all of it points in one direction. The exposed population is, by any honest reading of the data, more vulnerable to a 1995 class Omega block today than the exposed population was in 1995. That is not a forecast of mortality. That is a description of the risk profile. Whether the event produces 1995 class mortality depends on the duration of the block and the response of the systems that absorb the demand during the event. The near-term forecast question is whether the block holds for 5 days or for longer. That question gets answered, in steps, by the June 4th CPC update and the June 5th Drought Monitor update. If the June 4 update shows the Jeff's long-lived scenario holding over the ASM-F weakening scenario, the duration risk shifts upward. If the June 5th Drought Monitor shows ROD already registering in the soil moisture data across the Upper Midwest, the surface amplification factor I described in Part 2 becomes confirmed rather than projected. 2 data points, 24 hours apart, both due in 3 days. The 1995 record also contains a piece of context that doesn't usually make the headlines, but that matters for the current event. The Chicago heat wave was not initially recognized as a mass mortality event. Overworked emergency departments classified the first day's deaths one at a time as separate medical events, while the medical examiner's office processed them individually with no view of the accumulating pattern. It was only on day 3 and day 4, as the bodies accumulated, that the institutional response began to recognize the event as a public health emergency. The recognition lag mattered. Some of the deaths that occurred on day 4 and day 5 might have been prevented if the city had moved earlier on cooling center activation, welfare checks, and emergency outreach. That lag was a function of how the event was perceived in real time. The current event, if it materializes as forecast, faces a similar recognition risk. Heat events are not recognized as emergencies on the first day. By the time they are recognized, the curve has already accelerated. The lessons from 1995 produced documented policy changes in Chicago and other Midwest cities. Heat emergency plans were developed. Cooling center networks were expanded in many cities. Welfare check protocols for vulnerable populations were established in some jurisdictions. Those changes are real. They reduce mortality compared to a NOAA-sponsored scenario. But they do not eliminate it. The 2012 heat event in the Midwest, which had a Chicago area component, produced documented heat deaths despite the post-1995 policy improvements. The 2018 heat event in Quebec produced over 90 deaths in Montreal despite similar policy frameworks. Policy reduces, it doesn't eliminate. The base rate of mortality during a sustained Omega block over a populated area with vulnerable demographics remains significant, even with the best policy response. One last piece of the 1995 record belongs here because it directly connects to a piece of the current forecast. The 1995 Chicago event included a single specific day, July 13th, when the temperature reached 106 degrees Fahrenheit at the official observation station and the overnight low remained at 84 degrees. That combination, daytime high above 105 and overnight low above 80, is the specific condition the Whitman study identified as producing the steepest mortality acceleration in the data. The body cannot recover from a 106-degree afternoon when the night that follows holds at 84. The threshold for accelerated mortality in the published study was a 24-hour heat index average. When the 24-hour average crossed a specific value, the mortality curve steepened. That value, in the current events forecast, has not yet been projected. The CPC's discussion does not list a specific 24-hour average. The local NWS offices may begin issuing those products when the event window comes closer. If the local NWS offices issue excessive heat warnings for the June 8 through 11 window, with 24-hour heat index averages crossing the threshold, the operational response for hospitals, cooling centres, and welfare checks would activate. Whether those products get issued depends on the June 4th and June 5th updates I keep returning to. The agency has the framework. The framework requires the data to trigger it. The data is on the way. Everything in Part 5 describes what happened in 1995 to people who didn't know the Omega block was overhead and didn't know what it meant for how long the heat would stay. Part 6 answers the question this entire video has been building toward. What does all of this mean for you, specifically, right now, this week? Part 6. What this means. And that brings us to the thing this whole video has been building toward. Not the Omega block, not NOAA's models, not 1995. You. The specific question this part answers is whether you, or someone you know, or someone living on your street, is in the group that the CDC's own data identifies as carrying the highest mortality risk during a heat event, exactly like the one now forming overhead. The CDC's 2004 through 2018 mortality data, published in the agency's Morbidity and Mortality Weekly Report, confirms a specific statistic. Adults aged 65 and older represent 39% of all US heat-related deaths. That is the highest rate of any age group, at approximately 0.7 deaths per 100,000 population. The 1995 Chicago event, documented in the American Journal of Public Health study by Whitman and colleagues, identified 3 specific individual risk factors: living alone, lacking working air conditioning, being socially isolated from daily contact. Those 3 factors in combination produced a mortality risk nearly 3 times the baseline. You may be Margaret, you may be Harold, you may be Carol with the oxygen concentrator and the 4-hour battery. Or you may be someone who knows a Margaret, a Harold, or a Carol. The CDC's risk profile doesn't require living through 1995 to apply. It requires living alone, being over 65, and being in the path of an Omega block that NOAA's own models are calling long-lived. That profile fits millions of Americans in 12 states right now. The forecast is set. The window to act is 3 days long. The broader implications go past individual risk. The systems the viewer depends on are all simultaneously under stress during the June 8th through 11 window. The power grid, per NERSA's May 19th assessment, carries elevated blackout risk under extreme multi-day heat. Municipal water systems in the Great Lakes and Upper Mississippi Valley are entering the event with below-normal precipitation over the preceding weeks, which means reservoir levels and groundwater pumping demands are not at peak resilience. Hospital emergency departments in the affected states saw patient volumes increase by 35% during the 1995 event, according to Illinois Department of Public Health records. The same hospitals today have, in many cases, less bed capacity than they had in 1995. Now let me talk about what happens in the next 72 hours, because that is where the actionable information lives. The NOAA CPC Week 2 Hazards Outlook updates June 4th. That update will run the same model comparison the May 31 discussion did, but with 3 additional days of model data and observational confirmation. If the GEF's long-lived scenario is confirmed over the ECMWF weaker signal, the risk designation will upgrade. The upgrade path runs from slight to moderate to elevated. Each step represents a substantive change in the probability threshold and a substantive change in the operational guidance the agency provides to downstream products. The US Drought Monitor updates June 5th. That release will show whether the rapid onset drought has already begun registering in the upper Midwest. The Drought Monitor uses a 5-category scale. The categories are D0 abnormally dry, D1 moderate drought, D2 severe drought, D3 extreme drought, and D4 exceptional drought. The current map for the core heat zone is at D0 or no drought designation across most of the upper Midwest. If the June 5th update shows portions of Iowa, southern Minnesota, southern Wisconsin, or northern Illinois shifting from no designation to D0, the rod has begun. If those same areas shift directly to D1 in a single weekly update, the rod is accelerating faster than the typical 2012 style timeline. Those two data points, the June 4th CPC update and the June 5th drought monitor, released 24 hours apart, will define whether this event tracks toward the 5-day 1995 scenario or extends beyond it. The trajectory becomes measurably clearer after June 5th. Until then, the open question carries both possibilities. Let me lay out the two scenarios concretely, because the difference between them is the difference between a manageable event and a generational one. Scenario 1. The block weakens by June 12th. The heat event ends within the projected window. Cooling centers absorb the vulnerable population, the grid holds with margin, and the rapid onset drought registers as D0 in scattered pockets before the ridge finally moves. Agricultural losses stay below the 2012 threshold. The event becomes a notable summer heat episode, not a generational one. Scenario 2. The GIF's long-lived signal verifies. The block holds through June 20th or beyond. The rapid onset drought registers in the June 5th monitor and advances through the following two updates. A prolonged multi-system event unfolds across a 12-state region, with no relief mechanism visible in the near-term models. Grid stress accumulates day by day. Health system strain accumulates day by day. The mortality curve, following the 1995 acceleration pattern, steepens after day 3. The drought monitor map shifts into D1 and D2 zones by mid-June. Agricultural losses approach or exceed the 2012 threshold. The event enters the historical record as a major omega block event with documented mortality and economic impact. The probability of each scenario, as of June 1, 2026, is not equally weighted. The GEF's long-lived signal is currently the dominant model output. The ECMWF weaker signal is the alternative. Model agreement is closer to GEF's than to ECMWF as of the most recent run. That is not a guarantee. Model output can shift in 72 hours. The June 4th update will tell us which way the models have moved. The air is not moving, the water is disappearing, and NOAA just told you both in the same sentence. In 3 days, NOAA will release the number that determines whether this event tracks toward the manageable scenario or past it. That number will be a risk designation, slight, moderate, or elevated. And the difference between moderate and elevated is the difference between a forecast and an alarm. Let me put one more piece of practical context on what the upgrade path means. The slight designation, where this event currently sits, is a probabilistic flag for elevated risk. It is the agency's way of saying that the threshold for concern has been crossed and the public should be aware. The moderate designation, which corresponds to at least 40% probability, triggers more direct messaging from local NWS offices, including specific heat advisory products in many jurisdictions. The elevated designation, which corresponds to at least 60% probability, triggers excessive heat warnings in most affected local jurisdictions, activates cooling center protocols in many cities, and prompts utility companies to issue conservation requests. Each step up the ladder is not a small change. Each step represents a significant increase in the probability threshold and a corresponding increase in the institutional response. If the June 4 update lands at moderate, the operational response across 12 states begins immediately. If it lands at elevated, the response becomes a regional priority. If it holds at slight, the response remains at the current baseline, which is heat advisory language already issued by local NWS offices, but without the formal excessive heat warning trigger. The next 72 hours determine which of those 3 operational pictures the country wakes up to on June 5th. The actionable layer for the individual viewer is straightforward. If you are in the 12-state zone, check on the Margarets, the Harolds, the Eugenes, and the Carols on your street. The CDC's published guidance for heat events identifies daily welfare contact, with isolated older adults as one of the highest. Yield interventions for reducing mortality. That is not opinion. That is from the agency's published guidance. A phone call, a knock on the door, confirmation that the air conditioner is running, confirmation that the person knows to stay inside during the peak afternoon hours, confirmation that they have water within reach. Those are the specific actions the published guidance recommends. For agricultural producers in the affected zone, the actionable layer is different. The USDA's crop monitoring tools update on a different timeline than the drought monitor. The agency's NAS crop progress reports come out on Mondays. The June 2nd release will show conditions through the week ending June 1. The June 9 release will show conditions through the week ending June 8th, which captures the first day of the projected event window. Producers in the affected counties should monitor both the drought monitor and the NAS reports in parallel during the next 2 weeks. The 2 data feeds tell different parts of the same story. For utility customers in the affected zone, the actionable layer involves understanding what conservation requests mean if they come. Conservation requests from utilities during peak demand events are not legally binding in most jurisdictions. They are voluntary. But the cumulative effect of voluntary conservation across millions of customers can be significant. Reducing the load on the grid during the evening peak window, which I described in Part 3, is what often determines whether the grid holds or whether localized failures occur. The specific actions utilities request, raising the thermostat by a few degrees during peak hours, deferring laundry and dishwashing to off-peak hours, turning off non-essential appliances, are not symbolic. They are operationally meaningful. The window for all of these actions is the same window we keep returning to. The next 72 hours. The June 4th CPC update, the June FEFA drought monitor, the forecast confirmation, the forecast upgrade or downgrade, the institutional response activation. The window is short. The forecast is set. The data is on the way. There's one more layer worth putting on the table before the exit. The current event is not happening in isolation from broader climatological trends. The frequency of multi-day omega block events over the central United States has, by several published analyses, increased modestly over the past 2 decades. That trend does not predict any individual event, but it does suggest that the kind of pattern now overhead is becoming more common, not less. The 1995 event was treated at the time as a once-in-a-generation occurrence. The 2012 event challenged that framing. If the current event reaches 1995 class duration and intensity, the framing shifts further. 3 decades, multiple comparable events. The base rate for this kind of pattern is not what it was perceived to be in 1995. The implication is not panic. The implication is recognition. The pattern overhead is a recognized meteorological configuration with a documented historical record. The risk profile is well characterized. The vulnerable populations are well identified. The institutional response framework exists. What is missing in the current event is public awareness of the full picture. The headlines reported half the document. The other half, the ROD forecast, the slow-to-weaken language, the omega block mechanism, sat in the same paragraph and went unmentioned in mainstream coverage. This video has now reported all of it. What happens next depends on the June 4th and June 5th updates, and on the response of millions of individuals and institutions in the 12-state zone. One more concrete layer. The 12 states in the current CPC zone, with their combined estimated 7.2 million residents aged 65 and older, includes several specific cities where the 1995 mortality data has direct relevance: Chicago, Illinois; Milwaukee, Wisconsin; Minneapolis, St. Paul, Minnesota; Des Moines, Iowa; Cedar Rapids, Iowa; Madison, Wisconsin; Rockford, Illinois; Davenport, Iowa; La Crosse, Wisconsin. Each of those cities has a documented older housing stock, a documented older demographic, and a documented heat mortality record from prior events. Each of them is squarely inside the core of the current CPC slight risk zone. The risk does not distribute uniformly across the 40 million residents. The risk concentrates in specific neighborhoods of specific cities, in specific buildings, on specific blocks. Knowing your block is not panic, it is preparation. One sentence about what is not yet known and what is not yet decided. The atmospheric pattern overhead is identifiable. The model output is published. The historical analogues are documented. But the future state of the block, whether it holds for 5 days or 21, whether it amplifies into elevated designation or weakens back to baseline, is not yet fixed. The future is being determined right now by the upper atmospheric dynamics that the GFs and the ECMWF are simulating, by the surface moisture conditions that the drought monitor will measure, and by the demand response of 40 million Americans who will or will not act on the information now available to them. The atmosphere doesn't care what they do. The mortality data does. The grid does. The drought monitor does. The data is what closes the loop. The forecast is set. The window to act is 3 days long. The data points that resolve the open question, the June 4th CPC update, and the June 5 drought monitor are both due before the event begins. We will be tracking both. We will report back the moment the data changes. Here is where this story stands as of June 1st, 2026. NOAA's Climate Prediction Center has designated a slight risk of extreme heat for a 12-state region covering approximately 40 million Americans, valid June 8th through 11. The agency's own models show at least a 20% chance of temperatures exceeding the 85th climatological percentile across the northern and central plains, the upper Mississippi Valley, the Ohio Valley, and the Great Lakes. The GFS model has flagged this as a long-lived event for the full 2-week forecast window. The same document that contains the heat forecast also contains a rapid onset drought forecast for the same states, the same week. No mainstream news outlet has connected those two forecasts. The atmospheric mechanism sustaining both forecasts is an omega block. It is a stationary upper-level high-pressure system flanked by two troughs, forming a physical lid over the affected region. NOAA's own forecast language describes the pressure system as slow to weaken. The last time an identically configured pattern locked over this same region, more than 1,000 Americans died in 5 days. The 1995 mechanism and the 2026 mechanism are not similar. They are the same, different decade, same pattern, same geography, same vulnerability profile, by some measures worse. In 3 days, on June 4th, NOAA releases its next Week 2 hazards outlook. That release will show whether the models are converging on the long-lived Jeff signal or the weaker ECMWF second-half scenario. If they converge on the long-lived signal, the slight risk designation will upgrade. An elevated designation carries a 60% or greater probability of extreme heat, a threshold NOAA issues roughly 14 times per year. 1 day after that, on June 5th, the US Drought Monitor releases its weekly update. That release will show whether the rapid onset drought has already begun registering in the ground across the upper Midwest, before the heat event has even peaked. Those two data points, released 24 hours apart, will determine whether this story ends with a 5-day heat event or becomes something longer. We will be tracking both releases in real time and reporting back the moment the data changes. Subscribe to Rupture because NOAA's next hazards outlook drops on June 4th and the US Drought Monitor updates on June 5th. And we will be covering both releases the day they happen, with a full data breakdown of what has changed and what it means for the affected states. If the Omega block holds through the June 4th update, we'll say so, and we'll show you exactly what that means for the 2-week window ahead. If you live in one of the 12 states in the forecast zone, or if you have someone you care about who does, you'll want to know that number the day it comes out. Leave a comment below. Did you know NOAA's drought forecast was in the same document as the heat warning before this video? The story isn't decided yet. The forecast is published, but the verification arrives in stages. The June 4th update is the first stage. The June 5 update is the second. The peak of the event window, June 8 through 11, is the third. Each stage will either confirm the trajectory now visible in the data or shift it. Each stage will be covered here as it happens. The viewer who watches this video and acts on the information now available is in a different position than the viewer who waits for the local news to catch up. That difference between acting on the early signal and waiting for the late confirmation is what this channel is built to provide. NOAA releases its next forecast in 3 days. That number determines whether this stays at slight or becomes something the agency has only issued 14 times this year. We will be here when it does,